So, in calculus, finding a derivative is, well, it's a huge deal. But the official way, it can feel like trying to build an entire house with just one tiny screwdriver. Today, we're going to open up the whole toolbox. We're talking power tools that make finding derivatives fast, efficient, and, let's be real, way more fun. Let's dive in. Okay, if you've touched calculus at all, you've probably run into this monster, the formal definition of a derivative. And look, it's the foundation of everything, it's super important, but my gosh, using it for every single problem is an absolute grind. It's like, why would you take the long, winding country road when there's a super highway right next to you? Exactly. So what if there was an easier way? What if we had a set of shortcuts, a bunch of rules that let us just bypass that whole long limit process? Well, guess what? We do. They're called differentiation formulas, and trust me, they are about to become your new best friends. All right, let's start with the absolute workhorse of the toolkit. This is the one you're going to reach for again and again. It's called the power rule, and it is just beautifully simple. And here it is. It's that simple. If you have a function that's just x raised to some power n, its derivative is just n times x to the power of n minus 1. And the best part? That n can be pretty much any number you can imagine. Positive, negative, even a fraction. It just works. Really, that's all there is to it. It's just two simple moves. First, you take that exponent and you bring it down in front to multiply. Then you just subtract 1 from the old exponent. Boom, that's your derivative. And this example right here shows you just how much of a game changer this is. I mean, can you even imagine trying to plug x to the power of 1,000 into that limit definition? It would be a nightmare. But with the power rule, it's instant. The derivative of x to the 1,000 is simply 1,000 times x to the 999. That's it. Done. Okay, so we've got our main power tool. Now let's see how we can combine it with a couple of other simple rules to start tackling much bigger, more complex things, like entire polynomials. So, next up are a couple of rules that basically let us break big problems down into manageable chunks. First is the constant multiple rule. All this means is if you have a number multiplying your function, you can kind of just ignore it for a second, find the derivative of the function part, and then multiply that number back in at the end. And the sum and difference rules? Even easier. They just say you can take a function apart and find the derivative of each piece separately. And when you put these three rules together, the power rule, the constant multiple rule, and the sum rule, bam, you've just unlocked the ability to find the derivative of any polynomial. I don't care how long it is. You just go term by term. For x to the 8th, that becomes 8x to the 7th. For 12x to the 5th, well, that's just 12 times 5x to the 4th, so 60x to the 4th. You just take it one piece at a time. It's really that straightforward. All right, so handling polynomials is now a piece of cake. But what happens when functions get a little more entangled? You know, when they're multiplied together, or when one is divided by another? For that, we need to bring out the big guns, the master keys, the product rule, and the quotient rule. Now, before I even show you the right way to do this, let me show you the trap, because it is so tempting to think, oh, I'll just find the derivative of the first part and multiply it by the derivative of the second part. Nope, don't do it. It's probably the single most common mistake people make when they're learning this. And let's just prove it with a really simple example so you can see why. Okay, say we have x times x squared. We know that's just x cubed, right? And using our power rule, we know for a fact the derivative of x cubed is 3x squared. But what if we try that wrong guess? The derivative of x is 1, and the derivative of x squared is 2x. Multiply those together, and you get 2x. See? 3x squared and 2x are not the same thing. This proves that our first intuitive guess is just plain wrong. So what is the right way? It's this, the product rule. The pattern is, you take the first function, leave it alone, and multiply it by the derivative of the second. Then, you add the second function, leave it alone, and multiply it by the derivative of the first. It's a little pattern you just have to learn, and honestly, you'll get the hang of it super fast. And for division, we have this guy, the quotient rule. And yeah, I know, this one looks a little scary. You've got subtraction, you've got this squared thing on the bottom. It looks like a lot. But just like the product rule, it's a fixed pattern. Once you memorize it, you're golden. And to help you memorize it, there's a classic little chant people use. It goes like this: the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. Yeah, it's a mouthful, but I promise if you say that out loud a few times, it really helps it stick in your brain. And there you have it. In just a few minutes, we've gone from that one slow, tedious limit definition to a whole toolkit that lets us find the derivative of a massive range of functions. So let's do a quick recap of our new toolkit. We've got a rule for constants, the all-important power rule, a rule for sums and differences, the product rule, and the quotient rule. Honestly, with just these 5 rules, you are now equipped to handle almost any derivative they can throw at you in an intro calculus course.
Okay, these rules are cool and all, but so what? Why does any of this actually matter? What's the point of finding these derivatives? Well, let's look at a classic real-world application to see why. Motion.
So imagine you have an equation that describes a particle's position over time. We'll call it S. Now here's a fundamental idea in physics. Velocity is just the rate of change of position. And what's a rate of change? It's a derivative. So velocity is the first derivative of position. And acceleration, that's the rate of change of velocity, which makes it the second derivative. So using our new rules, we can just take the derivative of that position function to get velocity, and then take the derivative of that to get the acceleration. We just used our toolkit twice.
And once we have that formula for acceleration, we can plug in any moment in time to find out exactly what's happening. So for example, what's the acceleration after exactly 2 seconds? We just plug in the number 2, and we get a real concrete answer, 14 centimeters per second squared. Just like that, we went from an abstract polynomial to a real physical quantity. That's the power of this toolkit.
So, you see, these formulas, they aren't just a bunch of abstract rules to memorize for a test. They are powerful tools for solving real problems, whether you're in physics or economics or engineering. They give you the power to analyze exactly how things change. So, now that you've got the toolkit, what will you build with it?